Well, thank you very much for inviting me, in particular to give a talk. So my collaborators here are Julie and Jennifer Scully. All the nonsense that's in here is my fault. So I got involved trying to think about how long it would take for the potential impact-induced brine or cryomagma chamber beneath Occator to cool. And so this is the motivation. Of course, here's Occator Crater. We have these shiny salt deposits in the center that have been interpreted as sort of the volcanic extrusive products of this cryomagmatic activity. And so the setup here is these papers by Bowling et al. That model the kind of magma chamber that you get right after the impact. And the one thing to notice here is, so the reddish dark yellow colors are essentially above the melting temperature of pure water. So this is a tens of kilometer deep puddle of brine that's about, let's say, 5 kilometers wide. This, of course, is cylindrical. And then, everything that's sort of in the whitish colors, that is potentially above some sort of eutectic temperature. So this big hole of liquid brine is then surrounded by an even larger aura on the order of maybe 10, 15 kilometers width, where you could have partial melting occurring. And so the question that we were trying to answer is if this crater formed something like 20 million years ago, and these deposits are thought to be, geologically speaking, recent, could this magma chamber stay alive long enough to, if it formed 20 million years ago, to still be producing these extrusive products now. So that's what we're trying to explore, and the reason it was and so the other thing that's interesting that we're now trying to think about is this sort of amount of salts here is generally sodium carbonate, hydrated, I believe, but in the center there seems to be an increase in the concentration of ammonium chloride, so you can interpret this as a potential temporal evolution of the extrusive products, and that's something we would like to model. And that was the original motivation for this talk, but I don't have enough results for this, so I'm going to just talk about our current model and then more about brine mobility, since that is something that seems to be of interest here. All right, so our current thermal model was motivated really by 3 things in comparison to the work that's done before. We've realized that the crust likely has a lot of hydrates or clathrates in it, also has hydrated salts, and all of those have vastly lower thermal conductivities than your typical pure water ice. Of course, water ice itself has sort of the ability to self-isolate at high temperatures because the conductivity declines with temperature. And then we were also interested in including the latent heat release. And there's, given the enormous volumes of water that are involved here, there's a significant amount of latent heat. And so, how much do these 3 effects bias? And then the other question is, if the crust here is something like 40, 50 kilometers deep, and we have a tens kilometer deep hole and an even larger, partially molten zone, is there the possibility to maybe connect this shallow impact-induced magma chamber to a deeper brine reservoir that Quick and others have considered before? And so if that was the case, maybe then if this deep brine reservoir is overpressured, maybe it could recharge the shallow magma chamber or something like that. So the model for the moment is very simple. We start out just doing an overall energy balance, and then we partially differentiating the enthalpy, turn it into a simple temperature model for the moment. We assume, so currently the model doesn't have a feedback between composition and the amount of melting. We just have a prescribed temperature interval between some solidus temperature, which is assumed to be a relevant eutectic, and the liquidus, which is just a pure water melting temperature. And we assume that we have a uniform melt productivity across that. The latent heat essentially is incorporated in the sort of the effective heat capacity of the system. And then, so this gives it a heat capacity. It looks something like this. This is vastly, so the heat capacity is vastly higher in this partially molten region. And then we're exploring, in particular, the effect of how much ice versus hydrate there is in the crust, which you can see has a significant effect on the thermal conductivity of the surroundings. So I don't have access to the actual impact simulation results, and also there's all sorts of uncertainties in these, the size of the impactor, the thermal structure of the crust, all sorts of things. So I've tried to choose just an initial condition that is modeled after the simulation results. So there's a central region cylinder where we exceed the liquidus, and we can have some potential superheating. And then we have a just partially molten region around. And then I can just scale this, make it bigger, make it smaller. And then other than that, we vary the composition of the crust. And yeah, so what the superheating is. So if we let this evolve, so here I'm showing the maximum temperature. This red line here shows the region, where you have melt present, and this is just a volume as it declines. So this was significantly superheated here initially. One of the nice things that you see is so here, now we're only partially molten, so you see a lot of latent heat release that kind of stretches out the longevity of this crust, and then somewhere around 6 million years, everything has solidified. If we make it bigger, and we're getting, the other thing, maybe one way to think about the size of these magma chambers, we're talking about magma chambers where the energy required to take some sort of steady state thermal crust and then put that much melt into it is somewhere on the order of 10% of the kinetic energy of the impactor that has been assumed to form Occator Crater. So here we're getting, this is very large, so we're getting closer to maybe 15-20% of the kinetic energy. But what we can then see now, we're also tracking the lowest temperature. So the lowest temperature here in the lower crust, so this point, show this as blue. And if we evolve a very large magma chamber, then we can see that the lower crust will eventually here overcome the solidus temperature and create a potential connection between the impact-induced magma chamber and whatever deep brine reservoir there might be. And of course, if that is overpressured, this may allow a recharge of the shallower crustal brine reservoir. But of course, our model doesn't capture mass transport, so this is not included here. So then we can look at the timescales as a function of the initial superheating, as the amount of hydrate in the crust, and the size of the magma chamber, which I need to find. This is just a scaling parameter for this initial condition. I need to have something more useful here, like the volume or the energy. But you see that on the whole, by varying this three-dimensional parameter space, it's very hard to get past 10 million years for the longevity of this magma chamber. And if we want to create a connection to a deep brine reservoir, it needs to be a very large magma chamber, potentially larger than than is reasonable given the impact. But this all assumes that the brine just sits there and it just solidifies, right? And so I'm a subsurface person, and I'm mostly interested in what I would call flow and transport problems. So I'm actually, the aim here has always been to eventually allow the brine to move. So we haven't done that yet, but I want to just talk about some of the basics. So, in general, I think it's probably of interest for the whole cryovolcanism subject how mobile these brines are in the crust. And so Christine has mentioned this. One way of thinking about it is that if you had two ice grains and a brine melt pocket in between, then there's an angle at equilibrium here that is due to the surface tensions. And this angle essentially determines whether you have a connected melt network or whether you have a disconnected melt network. And if this angle is less than 60, then essentially at almost any melt fraction, you have a connected melt network. So you can kind of map this out. So this angle is here. It's essentially like a wetting angle. And here's the porosity or the melt fraction. And you see that above 60, we have this percolation threshold. So in this gray region, you have to build up brine to a certain amount of melt fraction before it connects and it can move. But if your brines if the dihedral angle is below 60, then there is, at least as long as the continuum assumption holds, there is no percolation threshold. And so the brines connect at extremely low melt fractions. And here's a beautiful example of one of these. This is a water melt network in polycrystalline ice. This is a microscopic image. And so here we're at less than 0.5% melting, but you have a beautiful connected melt network. This is pure water, of course, and I put this together before I saw Christine's presentation. But of course, the question is, would not a pure water, but a brine network, would that also have a low dihedral angle and also be connected? In all sorts of other systems, composition has an extremely strong effect on the dihedral angle. But I believe Christine has shown multiple examples of water, brine, water, salt systems where it seems that the dihedral angle is always below 60, which would suggest that at least if all the processes are slow enough that we can attain sort of equilibrium textures, then that brine should form a connected melt network even at very low melt fractions. The opposite example is, of course, what we've heard earlier today about sort of the freezing of sea ice, where you are very far away from equilibrium, you have all these non-equilibrium textures, and then you can retain salt. So if this is indeed what happens, if the brine does connect at low melt fractions, then it should actually be really mobile in these icy crusts. So we've looked at the permeability, so we have, So we've computed some of these melt networks, and then we've done flow calculations. And so there was a question earlier today about the permeability of these. This is for 1 millimeter grains here. And you see that the permeabilities, of course, are small, and as the porosity goes down to less than 1%, the permeability drops here orders of magnitude. So the permeabilities are low, but as I'll show in the next slides, these systems are very dynamic. So the porosity is evolving continuously in these systems. And so typically what happens is that the melt opens up the pores to the level that it needs to be able to drain, at a speed that is natural, that's given by Darcy's law. So if these brines do connect and form a permeable network at low porosity fractions, then we could have a behavior that is similar to this here. This is work that we've done in a completely different context, melt migration underneath mid-ocean ridges. And so here the melt is buoyant, but what we have here is a region with partial melting, and these golden or orange, whatever lines here they're supposed to be porosity contours. So it's essentially a Gaussian in porosity. So you have high porosity here. The gray is just a tracer that shows you where the fluid actually goes. And what you see here is in this case, the melt is buoyant, so it wants to migrate upward. And because there's a little perturbation here, it localizes into what we call a porosity wave, which then rises and it takes some of its chemical signature with itself. And so the assumption here is that the solid has a viscous rheology, right? And so what does that? So here's a zoom in sort of the last stage of this. So here we have what we call a nice porosity wave. So these are porosity contours. Here's a porosity profile through the center. And so the way this wave propagates itself is that the fluid in the top half of this wave is overpressured. And because the solid is viscous, it can dilate it, right? If the fluid is overpressured, it will just dilate the solid. And down here, the fluid is underpressured, and so the solid compacts. And because we assume a viscous rheology, it cannot resist this overpressure. There's no yield strength. So as soon as there's overpressure, you open up porosity. And I think this is actually quite analogous to some of the stuff that we've seen today or yesterday about fluid, cracks propagating itself due to the overpressure at the top and the underpressure below. So this is sort of a non-discrete porous media equivalent of sort of fluid propagation in a dike. And so it means you don't necessarily need to have a crack to be able to move the fluid, as long as the fluid forms a connected network, right? Of course, if it sits in isolated pockets, you can't move it. But as soon as it connects, you can have a porosity wave that essentially has the same thing. So it's possible that our little Occator magma chamber might actually, this is not a simulation, this is just Adobe Illustrator, might somehow move down, right? And I have no idea whether it would actually grow as it goes down because it gets to warmer regions and so on and so forth, or whether it continues to melt. But this is just something that I hope to explore in the near future. It's sort of interesting I'm not aware if anybody's actually sort of looked at this. If somebody has, please let me know. But if that was indeed the case, and it's based on that the brine connects at low melt fractions and that the crustal response is viscous. So this won't happen maybe at the very top unless you have a huge impact, which of course will warm everything. But it's certainly around a region where you're partially molten. Presumably the ice is reasonably soft, and there's at least some aspect of it that is viscous, even if it's not maybe linear viscous, but maybe more, some nonlinear viscous rheology. In case of the Occator here, it might allow connection to the deep reservoir earlier. Once it connects, of course, with an overpressured brine, you could drive this back up, maybe. I have no idea. In general, it allows, or will lead to downward transport of pockets of brine within the crust. So it raises the question is, whether you can actually maintain if your tidal heating or whatever it is creates localized melting in the crust, whether you can keep that there or whether it would generally have a habit of kind of draining downward unless you freeze it in time. It's sort of interesting to think of what this would do to the solutes that are in the crust. And of course, we've just had a talk about, so the other part that is not in this simple simulation of the porosity wave moving up, which doesn't have phase change, it's just a fixed amount of water, is here where if we're freezing the ice, of course, we're building up pressure. We're generating overpressure, and then there's two ways that the material could accommodate that. It could either fracture, or it could dilate the wall rock or the actual porous medium it sits in, and it's presumably if it's close to the surface, it will somehow balance these two, and the eruption could release some of that stress, and then if it's somehow it moves deeper just by cooling, right? Eventually, it might choose to propagate downward rather than erupting upward. All right, and that's it. So we've explored the cooling timescales with a fairly simple model right now that doesn't have a compositional feedback, but it does look at the latent heat and various nonlinearities. And it's it's very difficult to get the cooling time beyond 10 million years. But this is all without any form of transport, and so there's a question as whether these brines do percolate at low melt fractions. But if they do, then the problem becomes a lot more interesting or complicated depending how you look at it, and you may begin transporting things in either direction depending on which direction buoyancy or the overpressure goes. And with this, thank you for your attention.
So I asked Christine this question at the coffee break, and she said I should ask you.
I won't have to deflect to somebody else. Yes.
So if you like strain the ice over time and you develop some kind of crystal fabric, how would that affect these porosity networks?
So I guess there's what's called the shape preferred orientation, and then there's the lattice preferred orientation. We've looked at this naive version of shape preferred orientation, and so you make the permeability anisotropic, right, in the direction of stretching. And and the permeability anisotropy is significantly stronger than the amount of stretching. So a grain that's stretched by a factor of 1 point, where you start off with an isotropic grain and you multiply one axis by 1.3, this could introduce something like a 300-to-1 anisotropy in the permeability.
Yeah, so I was kind of wondering about how that might interact with a convecting ice shell.
So I haven't thought about this. My personal intuition is that if the brine is connected, it's very hard. So the brine velocity is generally order of magnitude faster than any kind of solid state convective. So I do mid-ocean ridge modeling, right? And so typically the melt rises at least an order of magnitude faster in the models than the solid, and the isotope data wants it to rise even faster. So melt is very mobile, and so I think it's extremely hard if the melt is connected to bring it up. So like a mushy dye up here, if it can drain it, it's going to be hard. At least that's what these models would tell. Now, if you freeze it in, or maybe because it's a non-equilibrium texture, you have you cut off the permeability at some point, then of course you can bring them up. Or you freeze it in. I mean, that's the other option, right? You just cool it below its freezing point.